Hi friends, in the previous class I have already explained about AM modulation. Today in this class I am going to explain Dsbsc, that is double sideband suppressor carrier. What is meant by Dsbsc? In Dsbsc, what you are doing is you are just suppressing the carrier while doing modulation. That is, in AM, we are transmitting carrier along with the modulated signal, whereas in DSBSC, we are transmitting only the modulated signal, we are suppressing the carrier. Let us explain about this. We know we know that the DSPSC signal is only the modulated signal. The modulated signal consists of message signal multiplied with the carrier. So S of t is equal to AC cos 2 pi fct into m of t. Now expand cos 2 pi fct AC into coefficient we consider as 1 into e power j 2 pi ct plus 1 into e power minus j 2 pi ct divided by 2 into m of t. As 1 in frequency domain will be 2 pi into del of omega. This is the basics in the signals and systems. So we are converting the time domain into the frequency domain. Then S of s is equal to AC into 2 pi into del of omega into e power j 2 pi fct plus 2 pi into del of omega into e power minus j 2 pi fct convolution with m of f. So we will get S of s is equal to AC by 2 into 2 pi into del of frequency multiplication. So del of omega minus 2 pi fc plus 2 pi into del of omega plus 2 pi fc divided by 2 convolve with m of f. As it is convolution property of the impulse function, AC by 2 into del of f minus fc convolution with m of f will give rise to m of f minus fc plus del of f plus fc convolution with m of f will give rise to m of f plus fc. That is, the spectrum is shifted towards right and left with a frequency of fc. That is, the normal message signal as the spectrum varies from minus w to w, as it is frequency shifted due to multiplication. So it will be like this. The spectrum is shifted on the both sides in the positive way as well as in the negative way. That is, it is shifted towards right with fc as center, fc plus w, fc minus w. Similarly, on the left side it will be minus fc plus w minus fc minus w. So from this we will find the bandwidth of the DSBSC signal. That is, bandwidth is nothing but difference between higher and lower order frequency. For the bandwidth we consider only the positive side of the spectrum, so it will be 2 into w. So the bandwidth of the DSBSC signal is similar as that of AM signal, and fc plus w is the upper side band and fc minus w is the lower side band. And now we will go for modulation techniques for the double-sided suppressor carrier. We have one of the modulation technique important for gate, that is balanced modulator. Let us consider the message signal is applied with a 180 degree phase shifter, then it will give rise to minus m of t. These two message signals m of t and minus m of t is given to the AM modulator, and at the other input of the AM modulator we are giving the carrier, that is AC cos 2 pi fct. What is the function of the AM modulator? AM modulator will take message as well as the carrier signal and produce the carrier signal as well as the modulated signal. So S1 of t is equal to AC cos 2 pi fct plus AC Ka m of t cos 2 pi fct. Here m of t is positive. And similarly S2 of t is equal to AC cos 2 pi of ct minus AC Ka m of t cos 2 pi of ct. Here m of t is negative due to 180 degree phase shift. These two terms will be subtracted, so we will get the DSB signal at the output. So output will be S1 of t minus S2 of t, that is equal to 2AC Ka m of t cos 2 pi fct. We are normalizing the Ka value to 1, where Ka is the amplitude sensitivity. Already we know that. We are normalizing to 1. So output will be 2AC m of t cos 2 pi fct. It is similar to the generalized equation what you know, that is S of t is equal to AC cos 2 pi fct into m of t. Now let us consider m of t as am cos 2 pi fm into t. Substitute in the general equation, then we will get S of t is equal to AC cos 2 pi fct into am cos 2 pi fm into t. So AC multiply and divide with 2 on both sides. We know that 2 cos A cos B is equal to cos A plus B plus cos A minus B. So AC AM by 2 cos 2 pi FC plus FM into T plus cos 2 pi FC minus FM into T. So the spectrum will be consist of both upper side band as well as lower side band, that is FC plus FM, FC minus FM with a magnitude of AC AM by 2. Similarly, we have the similar spectrum on the left side of the plane also. Now let us consider the power calculations. We know that total power in the Dsbsc, as you are suppressing the carrier, there is no need of power required for transmitting the carrier. We have only the modulated signal. In modulated signal also we have two components, upper side band as well as lower side band, and upper side band as well as lower side band. So from this upper side band as well as lower side band, from this we can say it is P total is equal to P upper side band, power of the upper side band component plus power of the lower side band component. From the equation ACIM by 2 cos 2 pi FC plus FM into T is the upper side band. Similarly ACIM by 2 cos 2 pi FC minus FM is the lower side band. So we know that power is nothing but Vrms square divided by R. Vrms square of the sinusoidal signal is equal to Vm by root 2 whole square. Therefore it will be ACIM by 2 root 2 whole square divided by R plus ACIM by 2 root 2 whole square divided by R. So total power what you are getting here is AC square AM square divided by 8R plus AC square AM square divided by 8R. So the total power is AC square AM square divided by 4R. Friends, I have done one mistake in the spectrum. That is, here we will get AC AM by 4. Okay, just change it to AC AM by 4. That's all. And what is the advantage of Dsbsc over AM modulation is power minimization takes place in the Dsbsc. Why? Because we are not transmitting the carrier, but in the AM we are transmitting the carrier along with the modulated signal. So we are minimizing the power in the Dsbsc because we are not transmitting the carrier. But what is the disadvantage? Disadvantage is the bandwidth remains same, friends. That is, bandwidth is 2W. Is there any problem in the higher bandwidth? Yes, friends. Actually, if the bandwidth of the signal increases, then the number of multiplexing of the signals will be decreases. In order to multiplex more number of signals through the channel, we require less number of bandwidth, which is essential. And we will go for efficiency, friends. Efficiency is nothing but utilized power divided by total power. The utilized power is the power which is given to the modulated signal having two components, upper side band and lower side band. Similarly, the total power in the Dsbsc is also the power for only the modulated signal. So efficiency for the Dsbsc signal is 100%, whereas in the AIM we have only 33.33% efficiency, remaining 66.66% of 66.66% of power is utilized by the carrier, which is not at all used. And now let us consider the message signal m of t and multiplied with the carrier having upper and lower components as AC minus AC. Now we will get S of t as a modulated signal. Here the modulated signal we will get is S of t. Here what is we have so many demodulation techniques. Let us try with the envelope detector. What is the what the envelope detector will do? Envelope detector will trace the peak of the amplitude of the modulated signal, because you are giving the modulated signal as an input. But actually, if you consider the peak value, envelope detector will be on only for the positive half of the cycles. So we'll get the peaks of the upper half. But actually the message signal is present in the peak of the one of the upper half as well as peak of the another peak of the lower half. So we are not what are the output you are getting at the envelope detector is not the actual message signal. So we are not going for envelope detector. So here the demodulation technique which you are using for Dsbsc signal is synchronous detector, as you are already discussed in AM modulation. In AM modulation, we are also used one of the demodulator technique as a synchronous detector, but which is not at all essential in AM, because we will use the envelope detector in the AM modulation. But here in the Dsbsc, we need the synchronous detector, which is the essential demodulation technique. And synchronous detector, here the input signal which is given is Dsbsc signal, and another signal to the product modulator is AC cos 2 pi FCT. V1 of t is the product of Dsbsc signal into the local oscillator. So we know the Dsbsc signal is AC m of t cos 2 pi FCT into AC cos 2 pi FCT. So we'll give AC square m of t cos square 2 pi FCT, that is V1 of t is equal to AC square m of t. We know that cos square theta is equal to 1 plus cos 2 theta divided by 2. So it will be AC square m of t by 2 plus AC square m of t by 2 into cos 4 pi FCT. This total signal is now given to the low pass filter. As I have already told you, what is the need of low pass filter in the demodulation technique is, as you want to recover only the message signal. The message signal is of low frequency in nature, so you are using the low pass filter. If you consider the terms V1 of t, AC square m of t divided by 2 is a low frequency signal, and it is having the message signal. And similarly, AC square m of t divided by 2 into cos 4 pi FCT, it is a high frequency component signal. So at the output of the low pass filter, it will take only AC square m of t divided by 2. Now we can able to recover or reproduce the message signal back. And it has some limitations too, as I have already explained in the demodulation technique of the synchronous detector in AM modulation. Let us consider it too. Assume that there should be a phase shift present in the local oscillator. Then V1 of t is equal to product of Dsbsc signal into local oscillator AC m of t cos 2 pi FCT into the phase shift which is present in the local oscillator is phi. So we are considering AC cos of 2 pi FCT plus phi. Now multiply. V1 of t is equal to AC square m of t divided by multiply and divide by 2 on both sides. We know that 2 cos A cos B is equal to cos A plus B plus cos A minus B. So we will have the terms cos 4 pi FCT plus phi plus cos phi. As now we are going to introduce to the low pass filter, it will take only the low frequency component, that is V1 of t is equal to AC square m of t divided by 2 into cos pi. And if pi is equal to 0, then we will get the V1 of t is equal to AC square m of t divided by 2. Similarly, you saw in AM demodulation also. If pi is equal to 90, then cos 90 is 0. So we will not get anything at the output. That is nothing but quadrature null effect takes place. To overcome this problem, synchronization is present. at the transmitting end as well as the receiving end. In order to synchronize the system, we require the essential hardware. It is somewhat costly in nature. Thank you, friends. In the next class, I will explain SSB signal. So keep revising the subject and remember and do the problems accordingly. I will conclude the problems after the completion of analog communication. Thank you, friends.